Okay, let's say you had a light that was giving off the full spectrum of color. So we'd pass it through the prism and we get this full rainbow up here. Don't mind these little dots, I think it's just from the picture. If you have a gas and you excite the gas, you electrify it, give it some heat, something like that, you pass it through a prism, you're going to get the emission lines. That's what we've talked about before. But if you have the full spectrum coming out of one source, and you have something that's relatively colder in front of it, what happens is, in that situation, you have the different energy levels. Here comes all this energy in, okay? The electrons will actually take and absorb some of the energy, so they will take it out of the rainbow so that they can jump up to a higher state. So in other words, when you get their spectrum, you're going to see these black chunks. That is where an electron actually sort of stole that kind of light in order to cause these different jumps. The neat thing is, these black lines correspond with the glowing white lines, or glowing colored lines of an emission spectrum. So you can actually look at an absorption spectrum, compare it to an emission spectrum, and you can actually tell what was in the cold gas in front of your full spectrum light. Okay, this is a way more simplified version of what scientists did. There's actually way more lines involved here, but I'm just going to show you. So they would look at the, let's say, the emission lines of hydrogen. They see, okay, on the colored thing, we get one here, 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 and here. And then they look at the sun spectrum, and they're like, all right, we have a black line here, here, and here, and here. So we know hydrogen has got to be in the sun somewhere. And you're like, wait, isn't the sun hot? How is that a cold gas? Well, yeah, but if you're talking about the core of the sun, okay, the outside of it is kind of shrouded in these gases, which, while obviously the surface of the sun is hot, compared to the core, it's much cooler. So that's why you get this absorption spectrum. And then they would go and they would look at sodium spectra or emission lines, and they'd be like, okay, we see some indicators of sodium here, so there must be a little bit of sodium in there. Magnesium, you get the idea. So this is how they can tell the spectrum of the sun. And here we actually have different stars and their absorption spectra. So you can look at the absorption spectrum and be like, okay, I see a dark spot here, and I see a dark spot here, and there's some dark lines here and here. And by doing that, you can actually identify, okay, those dark patches match hydrogen. These dark patches match helium. These dark patches match carbon. So what you can do is you can go through and be like, okay, this star must be burning X, Y, and Z. This star is burning X, Y, and Z. More complicated, bigger stars are going to be making heavier elements. So you're actually going to, generally speaking, see greater absorption lines. I don't know in particular, but you can see sometimes, you can see actually emission lines in some of these guys. I don't know about this particular star, but sometimes that happens when you actually have, here's like the star, and you have light coming towards you, and, okay, so here's like, let's do this, hang on. So you have the star, and there's the core of the star, and as it passes, so this was giving off full spectrum, full rainbow. As it passes through the outer layers, you're now having an absorption spectra come along. But you can also sometimes have what's called a nebula, which is a giant cloud of slightly warmer gases floating in space that may actually have their own emission lines happening here. So it can all kind of become a jumble. I don't know about this particular star and if that's what's happening, but I do see those little emission lines, and I wonder. Okay, I just want to show you one other cool little thing that you should be aware of. So here is the absorption spectrum from our sun. And here is the absorption spectrum of a galaxy. Let's just say, we'll make it simple. We'll just say it's a galaxy. Okay, galaxy again is a bunch, it's a big whirlpool with billions and billions and billions of stars. And they're talking actually about a supercluster. So they're talking about billions and billions of stars in one galaxy, and then many, many galaxies all in one. So, you know, if you're not feeling small right now, you're not paying attention. But anyway, this is the kind of absorption lines from our sun. And this is the absorption lines of something really, really far away. What do you notice between these guys? If you said everything looks like it's shifted to the right, you are absolutely right. This is called a redshift. And it's kind of amazing little thing. So do you guys know how when an ambulance is driving towards you, you hear this sound, it's like this, as a car passes you? Well, let me explain why that happens. So a truck or let's have our little ambulance here. It is giving off steady wavelengths in both directions. Oh, I did not draw those evenly. I apologize. Those should look the same. I will redraw them while making the annoying noise. That may be worse. I'm not sure. If the car or truck or whatever it is, ambulance, is coming towards you, it will, from its own perspective, be giving off the same number of frequencies every second. But if you're standing here, because the truck is approaching you, it's going to sound as though these frequencies are hitting you faster. So you will hear a higher pitched sound. When the ambulance has passed you, okay, it will, in its own sound system, it will sound like it's just going, but now you're still here. It will take a little bit longer for each frequency to hit you. So it will sound like ooh. So what you get is ooh. Same thing kind of happens with light. If you have an absorption spectrum and something's coming towards you, for example, the giant whirling Andromeda galaxy is actually coming toward us. Okay, that's a terrible galaxy. I apologize. It is giving off a steady frequency of light. Because it's moving toward us, or we're moving toward it, whichever one, you're going to perceive that frequency as being a little higher frequency. And therefore, you will see all the emission lines shift toward blue, or higher energy. If, however, a galaxy or whatever is moving, oh gosh, that's a terrible galaxy, is moving away from you, it will still give off the same frequency, but you will perceive it as coming to you a little bit stretched out, lower frequency. So you'll have a smaller frequency of light, and it will appear that everything is red shifted. If you are standing on the planet as our not so early astronomers who had figured this out were doing, they looked around and they started looking at all these galaxies, and they had what might be considered a pretty terrifying moment, because they looked around at all these galaxies out there, and they were like, okay, I wonder which ones are coming towards us and which ones are going away. And in fact, they found every single one, except basically Andromeda, was actually moving away. And the further it was from us, the faster it was moving away from us. So it is as though you're standing on an island in the middle of the ocean, and you look out, and all the other islands are retreating away from you. And the further you look out, the faster they're running away from you. It was probably a terrifying moment within astronomy. So the cool thing is, though, when you look at this is why this is happening. For a long time, this was baffling to scientists. Imagine space-time itself as basically a balloon. And you have space-time itself. And again, we're getting into some crazy stuff here, but I just think it's fun to do this. So you have space-time itself, all these little galaxies dotted along the outside of the balloon. It's as though the balloon itself, and again, nothing can exist inside the balloon. It's like we're all living on the surface of the balloon on our own little tiny galaxies. It's as though somebody is blowing up the balloon. So even though we're not like, as the balloon gets bigger, these little individual pieces get further and further apart. So they all think that they are moving away from each other, because they really are. It's not that they're flying away like a car. It's that space-time itself is actually stretching further and further apart. And I'm sure I just said like 8,000 things wrong with that, but that's the basic idea. That, my friends, is some evidence for the Big Bang.